Hello. The subject of our research is real-time vehicle detection and classification in UAV imagery using improved YOLOv5. Unmanned aerial vehicles or UAVs have become an essential technology for many applications. UAVs have high-resolution cameras, can fly over hard-to-reach and dangerous places, and record at various angles and heights. Vehicle detection and classification is one of the most critical tasks in UAV-based surveillance systems, and it has many applications such as traffic management, surveillance, disaster management, and smart parkings. Despite all of its benefits, detecting vehicles in aerial imagery has its own challenges, including objects appear very small, there are many shadows and occlusions, there are complex backgrounds which could lead to the objects being mixed up with the background, lighting conditions such as different weathers, and different orientations and altitudes. Object detection in general can be done using different methods which have progressed over time. The first methods were based on older computer vision solutions like a sliding window. The challenges mentioned before made classic methods ineffective, but with the advent of neural networks and later convolutional neural networks, the features of objects could be learned in a more intelligent way and better. CNN-based models are divided in two groups: two-stage methods like feature pyramid networks, regional CNNs, masked regional CNNs, and one-stage detectors such as single-shot multi-box detectors and you only look once. Two-stage detectors like our CNN first find objects using region proposal, then do classifications. Thus they have two stages. One-stage detectors like you only look once and single-shot multi-box detectors do objects localization and classification in one pass, and they treat the problem of object detection as a normal regression problem. Real-time detection is required in most real-world issues, thus high inference speed is important, and one-stage object detectors have a higher speed than the two-stage detectors, so they are more suitable for real-time detection. YOLOv5 is one of the state-of-the-art one-stage object detectors capable of real-time detection. YOLOv5 and other baseline models are developed and trained for general object detection, so we have to improve this model to be suitable for detecting objects in aerial UAV imagery. So our goal is to improve YOLOv5 to achieve a real-time vehicle detection in UAV imagery with improved accuracy compared to the baseline models. This slide shows the structure of YOLOv5. This model is broken into three sections: backbone, which is for feature extraction, neck, which is for feature map concatenation and aggregation, and head, which is for final object detection. The model includes different modules such as convolutional C3, which includes three convolution layers and pooling layers, special pyramid pooling fast, which decreases redundant parameters, and upsample, which upsamples the resolution of feature maps and helps keeping spatial information, and concat layers, which concatenate features from previous layers, and output layers, which make the final detection, which includes the position of boxes and their classes. The backbone extracts features using convolution layers, batch normalization, and the spatial pyramid pooling. Neck aggregates features extracted by the backbone from different stages, and concatenating feature maps from different stages reduces the spatial information loss due to many pooling layers. Head predicts feature maps at 3 different scales, which are 20 in 20, 40 in 40, and 80 in 80 grids. Predicting feature maps at multiple different scales helps to detect small, medium, and large objects in images. YOLOv5 has different variants which have the same structure but differ in width and depth. YOLOv5L and X are deeper and wider, and as a result have a better accuracy while they are slower. The light versions like M have lower accuracy but they have higher inference speed, so there is a trade-off between accuracy and inference speed. Multiple solutions for aerial vehicle detection have been introduced in recent years. Many solutions don't consider balancing accuracy and inference speed, which is our goal. Summary of some related works can be seen in the following table, including Wang et al. 2020 combined faster RCNN and feature pyramid networks for an improved accuracy. Zhang et al. In 2021 proposed a multi-scale adversarial network for vehicle detection in UAV imagery, which includes a Xiaomi CNN feature extract. And we improved YOLOv5 using attention mechanism and soft pooling. Our proposed method can be broken into 2 general modifications. The first one is a structural modification. The resolution and spatial information of feature maps is higher in the early stages, but features and information of small objects can be lost in later stages because of pooling. Our solution was to add an additional sequence of convolutional upsample, concatenate, and C3 layers to the next. So, especially the upsample layer can be helpful in maintaining the feature maps which have higher spatial information. Concatenating feature maps from the first C3 layer to achieve more spatial information was our solution, because as we said, the initial layers have more resolution and spatial information. Adding a new detection head with a set of 4 and specifically for detecting small objects was our other solution, which could lead to higher output grid size. So as a result, these solutions could improve the performance on detecting far and small vehicles. So our modifications can be seen in this image, which shows that as we said, we concatenated features from the first C3 layer and added an additional series of sequence of C3 convolutional upsample and concat layers, and added a new detection head for small objects. Our other solution was to modify model input size and depth and width. Higher resolution input size is essential and helpful for detecting small objects. Increasing the input resolution decreases inference speed drastically. Decreasing the network depth and width to make the model less demanding can be a solution. So we increase the input resolution by 60% to 1024 in 1024 pixels, decrease the depth multiplier of the network by 20% to maintain real-time detection speed. Modify the network width according to the depth was our other solution. All of the models were tested with the same hardware for a fair assessment and comparison, which the specifications of our hardware can be seen in this table. We tested the models on 2 different datasets: Vision Midstone dataset and the car parking dataset. Midstone has 4 classes. We chose 4 classes to test this dataset, and the car parking dataset has only one class and far less images and instances. So with their own images have more varied and more angles and altitudes, and they were recorded in very different conditions, like even in the night and in the day. But the images in the car parking dataset were recorded and captured in a fixed altitude and angle, almost 90-degree angle. So we first trained and validated our model and YOLOv5L for 50 epochs. The default input size, which was 640 and 640 pixels, was used. The depth and width modifications were not applied to only evaluate the effect of structural modification. With only the structural modifications, the proposed model has 5.4 more mean average precision 50, which means when the predicted box has at least 50% common area with actual box. So our test on the Wisdom test set shows that our model has more precision, more recall, and more in mean average precision 50% and mean average precision 95%, which means that the detected bugs and the actual ground truth bugs have at least 95% share area. So it can both classify and detect boxes more accurately than even the YOLOv5X, which is a much heavier model. Since the car parking dataset is less demanding, all of the models performed well, but our modified model has a higher mean average precision, 95% metric, which means that it predicts slightly more accurate boxes. For testing the speed of the model, we tested it on an 30-second long full HD video, which its screenshot can be seen here. And our model has it has less size and less floating point operations per second than YOLOv5L and X, and a little more than YOLOv5M, and its speed is also higher than these two and a little more than FPS, which because the real improvement is that it has more balance. It has both more accuracy and more speed than YOLOv5X, and while YOLOv5M has far less accuracy, while it has slightly more frames per second. This comparison shows that our model can detect vehicles in a real-world image better, especially in the corners of the image. And this image shows that it performs far better in situations where the objects appear very small, which in this real-world image. In conclusion, in this research, an improved version of the YOLOv5 model was proposed for vehicle detection in aerial UAV imagery. The neck of the network was improved for better feature map concatenation. A new detection head was added for detecting small objects. The depth and width of the model were modified to balance the accuracy and inference speed of the model. The results show that the proposed model is less complex and lighter and achieved 3.7% higher mean average precision 50 compared to YOLOv5L. Its inference speed is also higher, which is 6.1 frames per second faster on the same tested high definition video, and has 44.6 megabytes of list size. Thank you very much for your attention.